Hello guys, this is Kautam Balachandran. I'm starting the tutorial series for NVIDIA Triton Inference Server. As a part of this tutorial series, what we'll do is we'll use Triton Inference Server to the maximum. We'll see how to deploy models, how to do inference with models, what is KV caching, how is it used at inference, how to do this in GPU, right? How to use multiple GPUs, how to optimize GPUs, right? We'll see all of that, and including how to benchmark and monitor each of these models. But today's lab session, right? I've split this into 6 lab sessions, but today we'll specifically focus on TinyLlama. What we'll do is we'll deploy this TinyLlama onto a GPU server. The GPU server itself is something that I have rented out. So I've hired a GPU from Jarvis Labs. So I'll show you. Wait, I'll log in, and you can see this is the instance that I'm currently running. It's an L4 instance that comes with GPU. What I've done is from VS Code, I've done a SSH, right? I'll also show you, right? NVIDIA. You will see the GPU configurations, right? So from VS Code, I've directly done an SSH, and you can rent this, and the approximate cost is, I think it is 45 rupees per hour, which I think I was able to manage, and hence I've used it. You can set up your SSH configuration in the settings of Jarvis Labs, and then you can connect it from your VS Code. Now what we'll do today is I'll download the NVIDIA Triton image. You can see that this is the page, but please make sure that you create an API key from this site, and you can download the NVIDIA image specifically, right? And you'll have to download 2 images, although I would say the second image is quite optional. But you'll have to download the Triton server. I've downloaded 24.01, but I think 26.05 is the latest one, but I'll leave that up to you. And you can also download the 24.01 Py3 SDK, which we could use it for perf analyzer. That is, let's say that you wanted to benchmark your LLM, we could use this SDK, but I'll also show you how to do that without downloading this SDK. Which can save some space for you. So the very first thing that you'll have to do is I'll show you, right? So first you'll have to authenticate yourself, right? So you make sure that in your image, right, from the Jarvis lab, make sure you have the Docker installed, right? You can see that the Docker is installed, and then what you'll have to do is you'll have to do Docker login and then nvcr.io, right? Once you do this, it will ask for an API key. So the default authentication, since I've downloaded this already, I'm not showing you, but don't worry, you don't have to note down everything that I just tell you, because anyways I'll make the lab manual available to you so that you can go through the lab manual and do it at this in your leisure time, right? So you don't have to note it down, but the moment you get the access to the server, you will have to do Docker login, and there is a default authentication, that is the default authentication username, which is $OAuth token. Once you do this, it is going to ask you for password. The password is nothing but the NVIDIA API key, which is something that you can get it from NVIDIA by going to API catalog for free. You don't have to pay anything. You can I've included this API key for 12-month period, right? You can create your own API key, and that is going to be the password for login. Once you're done with logging in, you will have to pull the Docker image, Docker pull nvcr.io/NVIDIA, and then this is the image, like I said, right? I'm using 24.01-Py3. That's it. This is going to be the Docker image that you would be pulling after you authenticate yourself. And then once you are in, right, once you've pulled the image, what you have to do is we'll have to create the model repo, right? You can see I have created this particular folder called Triton LLM Labs. Once you get inside that folder, this is going to be your lab structure, folder structure. You will have three folders, model repo. I'll walk you through each and every one of these, so don't worry. And then what you do is you'll have to make sure that you download TinyLlama, and you will have all the details of TinyLlama, that is the model files under model underscore weights. And finally we'll be creating a Docker file with all the dependencies that we would require to run this. Now if you look at it, I have 4 folders, right? Tokenizer, TinyLlama, TinyLlama pipeline, and detokenizer, TinyLlama pipeline, and tokenizer, right? Once you complete this exercise, you will have to make sure that all these 4 models separately they run. If you look at it, each of these folders will have its own model file except for TinyLlama pipeline. It'll just have a config.pb.txt. I'll walk you through all these files so that you understand what is that we are doing, right? I'll start with tokenizer. So what is tokenizer, right? So it is nothing but before I give any input to the model, the words, right? For us humans, it is going to be words. For the model, it is going to be just numbers. What this tokenizer does is it will use the model file and it will convert these input string into numbers that the model can understand to build the attention. Now I'll walk you through the steps, right? If you look at the model.py, this is the code to convert your text into tokens, and you can see that we have given the model path and the string value, right? And we have made sure that the string value doesn't cross 2048, and we are also doing a padding, right, just in case if it should fall short, but we are doing it at the left, right? And we are also attaching the system prompt. That is what is that we'll be giving as a system prompt to the model along with the user prompt, right, so that it understands. You can see, right, we are giving the text input which is getting converted into bytes. So and then bytes is what we'd be giving, right? It's based on byte pair encoding. And finally we are converting this tokenizer. We are using this method to convert the byte pair into tensor, right, where we'll have the IDs and mask. Input IDs is going to be the encoder value, and we'll also be calculating the attention mask, which is what we'll be sending, right? It will have IDs and attention mask together. Now one question, right? So I was telling you that we'll be deploying this model in GPU, right? But for tokenizer itself, you don't require GPU. The reason being, tokenizer is nothing but a lookup table, right? You give a string, correspondingly we'll break down that string into smaller parts, and that will be converted into number by simple lookup. Since this is a simple lookup and it does not carry any quadratic operations, we don't require the tokenizer. Now the same is also going to get applied for detokenizer, right? Detokenizer is we give the output as a number, and that has to get converted to a human readable string. Only then it will make sense for us, right? So I'll also show you, right? Again, this has a model file, right? You can see that it is going to accept IDs, right? And you can see that it is getting decoded into text, right, which is what would be given as an output. Now each of these detokenizer and tokenizer will come up with its own configuration file. So this configuration file is what would be referred to encode and decode, that is to tokenize and to detokenize. If you look at the detokenizer, the input is going to be the output IDs from the last layer, and then you will see that it is getting converted back to text output to a human readable form, and you can clearly see the kind is going to be CPU. When I say kind underscore CPU, we are saying that for the server, right, when we are deploying it, we are saying do not use GPU. for tokenizer or detokenizer. The reason being, like I said, it is just going to be a simple lookup, right? And we are setting the batch size to be 8, right? I will also show you single inference, and I'll also show you the batched inference, right? But this is going to be the configuration for both tokenizer and detokenizer. And then comes the model, right? The model itself again will have a model pi. This is where we basically set up where should we look for the model, right? We have hard coded this model, right, to look for under model underscore weights directory. And you can see that we are also specifying what should be the input and what should be the mask, and we are also setting up other configuration while we are inferring. So you have what should be the maximum number of new tokens that is going to get generated while we are doing the inference, and we are also setting the temperature and top P, right? The discussion on temperature and top underscore P is out of scope for this particular tutorial, but I would suggest you go read about it. Temperature is going to set what is going to be the randomness in terms of generating new tokens, and top probability is going to basically dictate the model on which particular token to predict in a probabilistic fashion, right? So this is basically the model file under TinyLlama, right? And we are also using the garbage collection for the model, right, when it gets unloaded, because once you start deploying this model, you should see the ready part, model being loaded and ready for inference, and once you close this out, it will automatically get unloaded. And while it is getting unloaded, we'll have to make sure the garbage is collected so that we can utilize the GPU very efficiently. And secondly, like I said, right, you don't have to understand each and every line that I'm talking about. I'll give this as a lab manual. You can verify this later. I'm just going to give you the outline of what is that we are trying to achieve here. And you have the TinyLlama pipeline where we'll stitch everything together. That is tokenizer, detokenizer, and also the model itself, right? So the flow is going to be, I send an input string which will first get tokenized using CPU, again a lookup, and then that will be sent to model for generating from the input. It has to generate its own inference, right? Now the model itself is going to get deployed in GPU. Like I said, right, we'll have to do a lot of tensor operations parallelly, right? We cannot rely on CPU because the model itself could have multiple layers, and multiple layers could have multiple attention blocks, and these attention blocks can be handled independently for the purpose of parallelism, and therefore we are deploying this model for inference in GPU and not in CPU. Now once the model is done doing its inference, it is going to generate the output IDs, which is what will be used for the detokenizer, and the detokenizer is going to get the output IDs and convert them back to the human readable string. Now, like I said, right, the detokenizer is again a lookup task, and it does not require any support from GPU. So we will be using CPU for both tokenizer and detokenizer, thereby decreasing any load on GPU. We would only be using GPU for purely inference purpose. And you can see that it does not have any model.py. We can directly use the configuration. So this is where we stitch everything together. You can see that the input is going to be string, right? The input and the system prompt is going to be string, and what is the maximum token that I'll be generating, the temperature and the top underscore P that I just explained a couple of minutes back. And then you can see first we'll go to tokenizer. Input map is going to be text input and system prompt. The output map corresponding to input and system prompt is going to be output IDs and its respective attention. And then we give this to TinyLlama model for which the input is going to be IDs and attention mask. And then what happens is, again with all this in place, the new tokens, temperature and output P and output IDs, which is what we saw. It will then generate the output IDs as output map, and then output ID will be given as an input here, to the detokenizer, and again the output corresponding to output IDs will be looked up, and then text output is going to get generated. This is the whole operation, right? I think I was clear on this. What we'll do is you'll have to create a Docker file of the whole project. You can see I've created a Docker file just to make sure that the dependency issue is not there. You can easily manage all the dependencies. You can see from this Docker image I'm trying to install everything. You can also get into the Triton server Docker and then try to install it, so that you wouldn't have any dependency issue, but this is much more cleaner way of doing it. You create a Docker file and then you don't have to worry about what is that you would be facing as an issue later, right? So having said that, what we'll do is I've configured everything. We'll start the server. All right, so we'll do a Docker. I've already started this, so we'll do Docker start Triton LLM. Right, you can see that it is started, right? The Triton LLM itself has started. What we'll do is now we'll perform the inference, right? We'll perform the inference of this Docker, right? Once we create an image from this Docker file, all you need to do is start this Docker image, and from here on it means that the image is ready for inference. I've started another server, right? Another terminal, and I'll be giving commands for inference from this particular terminal, right? So you can see, right? You can see it is already started. Now what we'll do is I'll give the inference, right, in two ways. One, we'll do a single user prompt, and then what we'll do is we'll do a batched user prompt. I'll show you both, right? And then later we'll see how to benchmark this. Again, I don't want to type everything, although I could, but since it is a tutorial, right, I don't want to have the users watch my screen for a very long time just to look at mundane commands. I've already copied this. So if you look at this, right, I'm doing a curl and I'm doing a post since it's running in my local server, right? I'm giving this as a text input. You can see that this is just one input, it's not batched, and we'll see what it has to say. Yeah, you can see, right? You can see that it is giving a response, and it was pretty quick, right? So I was asking what is quantum computing, and it was saying quantum computing is a type of computing that relies on principles of quantum mechanics to perform calculations, so on and so forth, right? And since this is staged for me, and I think that this is pretty relevant to what I did ask the LLM. What we'll do next is I was showing you a single query, right, that I sent. We could also do a batched query. The way we do it is, this is how we do it. You can see that I'm appending, right? We can also append and ask something very controversial, right? What do you think about US politics, right? So let's see what it says. I mean, this is pretty controversial, right? So, but this is how you batch it, right? So yeah, I think I made an error. So yeah, 1 second. So it has to be 3.1 since I'm appending 3, right? Both sides of aisle making bold promises, taking extreme positions on various issues, it can be difficult to find common grounds. You can see that it is playing safe nicely, but apart from that, you can see it is giving very big responses for the batched input. So this is how we test for both a single input and a batched input, right? Next, what we'll do is we'll try to do a benchmark. Right, when I say benchmark, we'll give a short prompt, a medium prompt, and a long prompt, and we can see how to benchmark this, right? How the response would differ. What is the number of words generated? What is the average, or what is the time it took for the response, and how many words per second did it generate is something that we can look at right now. The way we do it is I've written a simple script. Again, this is part of the lab manual that I'll be giving you. You can see this is a very short prompt, this is medium prompt, and this is a long prompt, right? When I give this, it will basically tell what is the time it took in terms of latency, and what is the number of words it generated, and what is the frequency of words per second. It is a dynamic script, right, that I'm running here. So for the short prompt, the latency is this. It's responding in 1014 milliseconds. I think it's 1.14 seconds if I'm not wrong. It is generating, it generated 63 words, and you can see per second it is generating 62.1 word, right? And you can see slightly larger for medium and long. So this is how we do the benchmarking in Triton Inference Server. I hope the structure was clear. I hope the input and output was clear, and I also hope the benchmark, how we benchmark, and what metrics we monitor is also clear. Now again, all this is available for you in the lab manual, which I'll be sharing in the description field. So please do go over it, right? And in case if you have any doubts, please do leave that in the comment section. I'll make sure that I answer all your questions. Thank you.